Okay, so this is a quick set of notes about using finding a confidence interval. About the mean for the mean of a population. Typically, in this setting, what would happen is you would extract some data, and then from that data, you would be able to get two parameters, namely the mean of the sample and the standard deviation of that sample. Now, the problem here is that when the conditions for inferencing are being met, which are random, 10%, in either a normal population or CLT, right? So sample size of 30 or more. Normally we would fall back to normal with a mean at the population mean and a standard deviation of square root over, or sigma square root of n over square root of n. Now, granted, the population mean is what we're trying to estimate, so we're going to logically just make x bar the stand-in for that. However, this is a bit tricky because we don't know this, okay? And the sample standard deviation could be like widely different from the standard deviation of the population. So what we do is we fall back from the normal to what is called the t distribution. And it's actually a set of distributions depending on your sample size. So the t distribution has a thing, and it's kind of a little bit technical, and I don't want to get into the depth of this right now. It has a thing called degrees of freedom. And the flatness or roundness of the t distribution is actually determined by how many of these degrees of freedom that you have. So that's kind of like its relationship to the normal curve is how many degrees of freedom are we allowing, and kind of works out that way. If you kind of play this out, the more degrees of freedom that you have, the closer that this becomes to the standard normal curve. So we count the number of degrees of freedom as, so degrees of freedom will be the sample size minus 1. Okay, so let's say we took a sample of humans and we found their heights, and we said that the mean height was what do you call it? 5'9", right? So that's going to be like 69 inches, with a standard deviation in that sample of 2.5 inches. Okay, and let's say our sample size was that we took a sample of 100 people at random, right? Which means that my degrees of freedom for this problem is going to be 99. Okay, which is pretty high. Okay, so the next thing I want to apply here is a degree of confidence, right? So my confidence level. So let's say I want a 95% confidence interval. Now, we've worked out before, like, how to get the z-score from 0.95, right? So we need now not an inverse z, but an inverse t. So we need a t star here. Okay, so I'm going to bring up the calculator here for a moment, right? And clear this out and say, okay, so I want to take, all right, so if I have 0.95 as my degree of confidence, my error is 0.05. I divide that by 2, I get 0.025. Instead of inverting the norm, right, I'm going to actually go second vars, and I go invert t. Aha, there it is. So I want a 0.025. My degrees of freedom are 99. Because I have 100 in my sample. I paste, and this is going to give me a value. So the value here is going to be 1.984. All right, so my t star here is 1.984. Okay, so I have that. That's kind of like my standard score, right? Now I need something to stand in for the standard deviation here, right? So in my confidence interval, what I'm going to get here is, instead of using sigma over the square root of n, I'm going to use sx over the square root of n. So in this case, this is going to be 2.5 over the square root of 100, which would be 2.5 over 10, which would be 0.25. Okay, so my confidence interval is going to center at that 69, and I'm going to throw the t at 1.984 times this 0.25. So let me kind of write that out a little bit. Okay, so the confidence interval here is going to be my point estimate, which is the x bar, plus or minus this t star times the standard deviation of the sample over the square root of n. So in my example here, I had an average, and my sample was 69 inches. My t star became, let's double check that number, 1.984. And then I took standard deviation, which was 2.5 over the square root of n, which was 10, so that was times 0.25, right? So let's kind of work that. If I go 69 minus 1.984 times 0.25 gives me 68.504. So 68.504, right? And then I'm going to do this again, and I get not minus, but plus, which is 69.496. 69.496. Okay, so this is one of all of the confidence intervals that I could get from all of the samples size 100 that I would take from the population, and 95% of those confidence intervals would contain the actual mean of the population. So I have a 95% chance that this is one of those confidence intervals, right? So I can be 95% confident that this particular interval contains the mean of the population. Another way to attack this same problem is to let the calculator do the work. So if I go stat tests, now I have a t interval. That's what I want, t interval. So I'm actually going to put in the stats, right? You can actually just throw in a data list and it will extract the sample standard deviation and sample mean for you. But I'm going to give you the stats. In our case, the mean was 69. The standard deviation was 2.5. My sample size was 100, and I had a 95% confidence level. So it already went ahead and calculated like the degrees of freedom for me is 99. And if you look, I got 68.504, 69.496, 68.504, 68.496. The calculator and I are getting the same interval, right? So that's all great. So remember, because we don't know the standard deviation of the population, we have to drop back from the normal assumption down to using this weird t distribution set, and you can actually create a confidence interval. So there you go.